Yours. Thank you.
So, thank you very much, and a warm welcome from my side. My name is Thomas. I'm a product manager at MicroEpsilon. I have a look today at two measuring principles. One of them is the deflectometry, and one of them is wavefront sensors. And we want to tell you about how it is possible to detect components and optical parts with these sensor systems. So nowadays, unfortunately, a lot of transparent and highly reflective surfaces are still inspected by the human eye. So this is a very employee-intensive, a very work-intensive, and a very feature-intensive job to do. So what we want to do now is have the opportunity to do an automated visual inspection on transparent and highly reflective surfaces. So the thing here is, by doing such an inspection with a sensor, you automatically get a protocol which can use or the customer use, and so the manufacturer and you have the same common database. So this is a little bit about my motivation today. So first of all, you already passed through the motivation, so it will be a little bit shorter now. And what I want to show you next is what is MicroEpsilon if you don't know the company yet. Then I want to talk about the Scheck-Hartmann sensor, about our reflect control sensor, and then we did some measurements on optical mirrors. And then there's a comparison between the two sensor principles. And in the last point, I want to do a short summary here. So who is MicroEpsilon if you don't know us yet? We are a German technology company, mostly focused on sensors and systems for solutions for the customer. And our principle here is more precision. So for you, if you don't know what we are doing or what sensors we have in the portfolio, we have laser triangulation sensors, we have confocal chromatic sensors, white light interferometry, capacitive sensors, eddy current sensors, inductive, magneto-inductive sensors, and also draw wire sensors. But there is still more. So we have also 2D, 3D line scanner, 3D snapshot sensoric, measurement systems, and optical micrometer, fiber optic sensors, color sensors, thermal imager, pyrometer, and also laser distance sensor. So there's quite a broad portfolio, as I would say. But let's talk about the two sensor principles I want to show you today. So first of all, I want to give you a small insight into our wavefront sensors here. So the easiest way to describe a wavefront sensor is via light source, which has a wavefront which comes out of it. And next, you could say the wavefront, if it is far away from the light source, becomes a plano wavefront in this case. Then you have an optical system where the wavefront passes through. And after this, passing through the defined optical system, you have an aberrated wavefront. And this aberrated wavefront now can be detected by a Scheck-Hartmann wavefront sensor. So let's have a look inside such a sensor. So in our case, on the bottom side, you can see there is the Scheck-Hartmann camera with the wavefront sensor integrated. On top of it, you have the fiber light source, where you can use a laser diode or an LED, whatever you want. And then you pass the light through the system by telescopic objective, by various objectives inside. And what you get is a high quality output beam. On the right hand side, you can also see an image of what this will look like in reality. So we had a look at the inside. So the inside always stays the same. What you now can do with it is by doing a double pass configuration, you could do different setups. And with the different setups, you have different opportunities to measure measure on spheric, on flat surfaces, lenses, telescopes, binoculars, and so there are different ways of detecting measurement objects here. So in the test configuration, the reflective light can be tested. You have a double pass testing here, and there are a lot of different samples which can be tested by such a sensor. So you could use it for mirrors, you could use it for objectives, binoculars, and also we have a system which has a high performance here. So we can measure with up to 10 Hertz. We have an output beam which is approximately 20th of lambda. It is easy setup and can be easily integrated and set up here. The other system I want to show you and shortly talk about is our reflect control sensor. It is based on phase measuring deflectometry. So what we have here is a system which works with a screen which is protecting a sign pattern on your reflective target, and with two cameras we then can create 2D images based on the camera images, and also create a 3D point cloud by laying both of these areas on top of each other. What this looks like is presented here. So we start with our sign pattern on the surface, which generates the different images for us. And what you get is on the first place an amplitude image, where you can have a look at the reflectivity of the surface, a curvature image which describes the surface as it is, and on top of it you also get a 3D point cloud of your reflective surface. A measurement time here is approximately 2 seconds, and the processing time afterwards will take another about 3 seconds here. So the 2D images you get, this is an example of the battery industry here. So the system works because all of these batteries have a slight foil on it, and the foil is reflective, and so we can measure with the reflect control here. The first place you get, as we call it, base intensity image. So the base intensity image is more or less what you get from a normal high-class vision system. So in the first place you might think there is no failure on top of it. In the second step we also get an amplitude image. In the amplitude image, as I described, you get an impression of the different reflectivities of the surface. So for example the fingerprints which are on top now can be seen quite good. And then in the last step you also get the curvature image. And the curvature image is for detecting any difference in the surface normal here. So as you see, you wouldn't see the scratch which is in the on the battery on top without having also the curvature image here. And what we also can do now is everything which can be seen in our curvature image can also be transferred into a 3D point cloud. And by transferring it into a 3D point cloud, you can also do a measurement with it and perhaps measure the depth of such a scratch. So much to the second measurement principle I wanted to show you here. And now we had to look for different measurement objects which can be measured with both systems. So in the first place, the wavefront sensor. So we had to look for some smaller targets here, and in the second step with the reflect control sensor, where we have to have a very shiny or reflective surface. So we came up with 3 different mirrors. The first mirror we measured was a mirror with a gold finish and peak to valley with lambda 4th. The second one was a planar made of Zero Dur with aluminium finish and had a surface which was lambda 10th. And the third one was a little bit bigger mirror with 25 millimeter in diameter and a peak to valley of lambda 1. So what we did here now is setting up a test series and we did 4 or 5 measurements while the mirror stands still to have a look at the repeatability of the systems. And also we had 4 measurements where we turned these mirrors always by 90 degrees, so we can also say how reproducible the systems work. All PV values, which I will show you now, are rounded to full nanometer, and when it comes to the RMS value, it's rounded to a 10th nanometer. So the first thing we had here was the measurement with the reflect control system. So as you can see, the reflect control system is also able to measure a peak-to-valley value in the nanometer range. So we can go down to 10 nanometer approximately, and we are very stable in the measurement itself. And the RMS values also are really quite stable here. Same thing, more or less, when it comes to the Scheck-Hartmann wavefront sensor. So there is also high stability when it comes to the peak-to-valley values and also when it comes to the RMS values. There is a slight difference between the values you see of the reflect control system and the Scheck-Hartmann sensoric, but I will come to this point a little bit later on. Then the tests where we turned. I have to hurry up, I get a signal here. Okay, then we turned all the mirrors a little bit by 90-degree steps, and also here we are quite stable. And the next thing is we did it with the Scheck-Hartmann sensoric, where we also turned the mirrors by 90 degrees and get quite the same values here. So all in all, we did the tests for all the 3 mirrors. And what you can see here is that there are only slight difference between the measuring principles. So it is basically possible to measure on these mirror type surfaces with both measurement principles. And always, as it comes to vision systems, you get slight differences in a nanometer range. But I think we can show that both systems are able to measure on such surfaces. So pros and cons, perhaps we can talk about the pros and cons later on. Or a little deciding matrix where to decide what sensor type you should use. Perhaps one point here, the target size. If the targets get too big, use the reflect control. If they are a little bit smaller, just use the Scheck-Hartmann sensor. Is the first thing which you can have a look at. So what I wanted to tell you today is whenever you have a look at a transparent object like glass, foils or other plastics, high reflective surfaces like polished metal, a mirror, shiny ceramics and stuff. So please don't be like these guys. Please think about a quality control other than the human eye, because you wouldn't also want to do this job. So thank you very much for your attention. I think a little bit out of time, but if you have any questions, please feel free to ask. We are in Hall 10 and at booth 10. C30, and you can visit me there and ask all of your questions. Thank you.
Thomas.